Welcome back, class. Last couple of weeks we've been talking about inverse functions, and I want to bring back another type of function that does have an inverse, and we're going to talk specifically about what that inverse is. So behind me on this whiteboard right now is the inverse, or excuse me, the function, exponential function, y equals 10 to the x power. And so I also included a little table below so we can see what actually is happening in this function. As you put x values in here, from the x values in the table, the 10 is raised to that power. So I'll start with 0. If I put 10 to the 0 power in, 10 to the 0 power is 1. Let's watch the pattern now as I increase the values of x. If 10 to the first goes in here, 10 to the first power is 10. If 2 goes in for x, I have 10 times 10, which is 100. If 3 comes into the power function, I have 10 times 10 times 10, which is 1,000. So we can see the exponential curve, or exponential growth on here, is multiplying by 10. And as you increase in x values this way, we see that multiplication of 10. But if you reverse the process and start up here and come backwards from 3 down to 1, we can see that the y values could be given by a pattern by dividing by 10. Therefore, if you continue the pattern to the left, 1 divided by 10 would be 1/10. I'm going to include that here, 1 divided by 10. If I divide that number by 10, I would have 1 divided by 100, or to help us with this, 1 over 10 squared. If I keep dividing by 10, this becomes 1 over 1,000, or 1 over 10 cubed. Okay? So it turns out raising 10 to the negative powers give us these decimals, as well as 1 over 10 to the power, positive power of those negative numbers. So this is our exponential growth process with base 10. Well, what I'd like to look at now is what is its inverse function. Because we talked a lot about functions that need to have inverses. And this base 10 exponential will meet all the requirements of needing an inverse. It is a 1-to-1 function. If we graph that 1-to-1 function, we'll soon find, I'll plot 0, 1 here, you'll soon find that this curve looks a lot like this. So it's a 1-to-1 function, leaving only having one possible input for each of the outputs. But it also would pass the horizontal line test. There is no horizontal line that can pass through this curve that would pass more than one point. So it's a 1-to-1 function. Therefore, it has to have an inverse. Well, inverse functions require us to do a little bit of manipulation. So when mathematicians first started exploring this problem, they said we need an inverse function that when we put these y values in, we get out those x values. Well, in inverse functions, we switch the x with the y. So if I do that here, switch the x for the y, I'm going to switch to a new color here as well. If I switch the x with the y, I would have x equals 10 to the y power. Okay, well this would be our inverse function, but mathematicians like to have these solved explicitly for y. So we'd want to solve that for y. This poses a little bit of a problem. This is an exponent. In the past, when we tried solving for y, we could use our order of operations and do some multiplying and dividing, some addition, some subtraction, and we could solve that explicitly for y. This one, I can't do any of those algebraic manipulations. Therefore, mathematicians said, you know what, let's redefine this. Let's call this something new. Let's take this base 10 here, this y and this x, and let's call this a logarithm. So we're going to rewrite this logarithm as a logarithm, log is short for logarithm, with a base of 10, and that's in subscript, if you will. So logarithm base 10 of this number will equal y. These are equivalent ways to write a logarithm. Logarithm is defined such that the power is equivalent to the base of 10. 10 to that power is equivalent to x. This is our logarithm. And logarithms are the inverse to exponentials. Now on that line, we also know some things about this function before we even do anything else. Inverse functions, we switch the x with the y. Well, in the original expression y equals 10 to the x values were the domain of the function. These could have been any real number that we have listed. And the outputs were all of these multiples of 10. And all of those were positive real numbers. And on the graph, you can see that. We're allowed to go positive x values, we get positive y values. We have negative x values, we have still positive y values. And 0 as an input gives us an output of 1. So we have a functions whose inputs are any real number, but outputs are positive reals. For the logarithm, we switch those x and y's. We switch the inputs for the outputs, therefore switching the domain with the range. So in the logarithm function, these new y values become our inputs. These x values become our outputs. Therefore, the domain of the logarithm function would be only these positive real numbers, whereas the range could be any real number. The function would end up having a reflection across this line y equals x. And I'll put that line here in a minute, but I'm going to go ahead and sketch a quick graph of the logarithm. If I follow the pattern, I'm going to have this curve, the logarithmic curve. And it turns out that a function and its inverse are reflections over a line y equals x. So I'll kind of sketch this line in here. That's y equals x. I could reflect the 10 to the x exponential over the logarithm of the base 10, and they'd be reflections of each other. So the logarithm is invented by mathematicians to be the inverse of base 10 exponentials, but it's defined as this exponential equation itself. We're now going to use logarithms as an inverse function to help solve exponentials.